In this video, we discuss how to use AMPL, which is an algebraic modeling language which provides a user-friendly interface to major optimization solvers. First, let me show you how you can get the solver online. AMPL free download. There is a version for students, which you can download from the AMPL website. So this version is actually limited, so there is a limited number of variables and constraints that you can use, but you can download it at any time for your course projects and so on. You need to fill out the form and then you can download this software. The version provided in the distribution on eCampus is the free AMPL for courses, so this is actually a full-blown version of AMPL. But the downside here is that it's not going to work as soon as the course is over. All right, but this version has all the solvers that are included in the package, and there are no limitations on the number of variables or constraints, so you can play with it and solve some very, very large-scale problems. Okay, so let me go to the folder that you can download from eCampus. So I already unzipped it, and here is the AMPL folder, and there is also the folder with the examples that we are going to use to illustrate the software. So if you go to the AMPL folder, you will see the AMPL itself. So if you click on it, it will open a command window. All right, so here we'll type the commands to run the solvers that we want to run. You will see also many other executables along with AMPL. So there is, for example, Baron is the solver for global optimization, then ConOpt is a convex optimization solver. Gurobi is actually the solver that we are going to use, so this is considered to be the state-of-the-art solver for linear programming and also integer programming, as well as mixed integer programming. So there are several other solvers like Nitro, Minos, and so on. If you're interested in exploring this, feel free to check out the documentation for AMPL. So there is actually a free AMPL book, so you can easily find it using a search engine and just type free AMPL book, and you'll be able to download the PDF for it. So there are many different things that you can do with this, so the purpose of this video is just to give you a basic idea of how to start. All right, so let's try to look at the examples that I provided with the distribution. So this includes several very simple examples, just two examples in fact. There is example 1 and example 2, so let me copy all these files to the same folder where AMPL executable is. So we need this in order to run AMPL without specifying the path to the working folder. All right, so I went back to the AMPL folder, and now I'm going to copy these examples here. So let me open this example 1 file. So you can open it in any text editor. Well, the file has the extension .mod for model, so I guess Windows tries to use some movie software to open it, so we'll need to select some text editor to open the file. Open with, I need another app, it's not a movie here. So let's see if we can get an acceptable one. So for example, Notepad will work for our purposes. So this opens example1.mod file with the model. So we can see that it starts with a hashtag and decision variables. So whatever line starts with a hashtag is not going to be read by AMPL. So this is just for comments purposes only. So let's say here I could put, not just in the beginning, but in the end of the line I could put a hashtag and say first variable. Okay, so then we save the file. So we can see that we have 3 decision variables, x1, x2, x3, and all of them are non-negative variables. Next, we specify the objective. The objective is to maximize z, which is given by 4 times x1 plus 3 times x2 plus 5 times x3. Z is just the notation I decided to choose to represent the objective. So, but in general, I could say, let's say, objective value here. So I could use this instead of z. Okay. And then we have the constraints specified. So same thing with the constraints. We start the constraints with st, which is subject to, so I could actually spell out subject to instead. And then we have the notation for each constraint. So C1 represents the first constraint, and C2 and C3 represent the second and the third constraint respectively. So you can see that every line in an AMPL file, in a mod file, ends with a semicolon. So this is the syntax for AMPL. So now we have this mod file. We go back to the command window. So let me open AMPL again. And this opens the command window. And let me load this model to AMPL. So I type model. And remember, we saved this mod file in exactly the same folder where ampl.exe was. Because of that, I don't need to specify the path to the folder where my example file is located. So we type example1.mod and then semicolon. And this loaded the model into AMPL. So now to solve the model, all I need to do is just type solve. And we get the optimal objective value. So you see that the optimal objective value is 11, obtained after 2 iterations. In this case, we didn't specify the solver that we were using. It says here minus 551 found the optimal solution. So minus was the default solver. But in general, we can also specify the solver, and we can use any other solver in that folder to solve this problem. So remember, we had the folder with all of these executables that represented different solvers. So if, let's say, I wanted to use Gurobi as the solver, then I specify option solver and Gurobi. Now we need to solve the problem again. So in this case, you see the output is the same. So the optimal objective value is 11, but AMPL tells us that the problem was solved using the solver Gurobi 8.1.0. Usually, unless it is a very small model like this one, we represent a problem in AMPL using 3 different files. Okay, so in this example that we just considered, example 1, we only had the mod file that represented the model with all the coefficients, decision variables, objective, and so on. But if we have a larger model, let's say, or sometimes actually we may have similar constraints that we don't want to type out explicitly with the given coefficients, or we may want to solve the same model with different data, it's convenient actually to split the model into 3 parts. So let's look at the example 2 that we have in our folder here. As you can see, for example 2, we have 3 different files. So there is example2.mod, so this is a mod file. Then there is example2.dot, so this is a data file where all the data are stored. And the third file is example2.run, where we specify the commands that we could alternatively type in the command window, but it's more convenient to just type all of these commands in a separate file and then just load this file into the AMPL window and run everything from there at once. Okay, so let's look at what we have in this example. So the second example is actually solving the same model, but using this representation with 3 different formats. So let's open example2.mod. So we open it with a notepad, and again, you could use any text editor really for this purpose. So look, in this case, we actually use these sets and parameter notations to represent our data. So these are the sets that we use for indices. So assume that this was the problem where we were trying to optimize the production process. So we essentially assume that this model specified here on the slides, xj represents the number of units of product j to be produced, and then you have the objective coefficients, and the constraints represent the 3 different resources that you use to produce these 3 products. So if you have a model like this, obviously we have a clear physical meaning for all the variables and constraints, right? So it makes sense actually to represent the sets of these indices I and j. So we use j's for variables and I for constraints. It's convenient to represent them using these set notations that we see in this example2.mod file. So we have one set P for the products, and j is going to belong to this set, and then we have set R for the resources. So this is to represent the resource constraints. So in our case, for this particular problem that we are considering, we have the set P consisting of 3 products. So you can say that P consists of just 1, 2, and 3. And then the set R consists of 3 resources. So R also is given by 1, 2, and 3. But in general, let's say if you had more products and more resources, you could still use this model here, and then all the data would be specified in a data file, so which was example2.dat for data. So then you have the parameters. So these are the coefficients essentially. Okay, so the parameter C for each index j in the set P, in the set of products, will have Cj given, right? So this vector C of parameters will represent the coefficients for the variables in the objective. Okay, so then you have the parameter B for each I in R, you will have a BI value. So these are the right-hand sides for our model. So let's say for our problem, B would consist of 4, 6, and 8. And actually, let me open the data file at the same time so we can see how we represent this data in the dot file. Okay, so this is our data file. So we have, for example, for this parameter C, look, the way we define the data file. So here, first, you specify the set P. So instead of just j's, we use here the actual meaning of each index in this set. So remember, in the model we have j equal to 1, 2, 3. So, but in reality, what does j equal to 1 represent? So it represents product 1, right? So instead of j equal to 1, 2, 3, we use product 1, product 2, and product 3 for this set P. But again, in general, you could call this whatever you want. So you could just say P1, P2, P3, let's say, or just 1, 2, 3. So then you have the set R. It represented the resources. So again, we have set R represented the resources. So, and then you have resource 1, resource 2, resource 3. So if you had more resources, you could just specify resource 4, 5, and so on. And you would only need to modify the dot file if you are modifying the problem input, but the overall model would be the same. So then for parameters C, parameter C is for J is in P. So for product 1, the coefficient in the objective was 4, for product 2 it's 3, and for product 3 it's 5. So this is how we specify the values of these objective coefficients here in the dot file. And then you have the parameter B. So you see you declare them all in the model, but you specify the actual values for the parameters in the dot file. So for B is specified for each resource. So for resource 1, we have the availability of it was equal to 4. For resource 2, it's 6. For resource 3, it's 8. Now, the last parameter here is the coefficients that we have in the constraints. And in this case, we have aij's. See, we specify these parameters a for each I and for each j. So for I in R, for each resource and for each product, we specify aij, which gives us the amount of the resource I we need in order to produce 1 unit of product J. Most conveniently, this data is represented in the table like this one here. So for example, in this case, we specify each column that corresponds to the products, product 1, product 2, product 3, and then the rows corresponds to the resources. You can see that we essentially copied here this table that corresponded to the data in this problem. So 1, 2, 2, 3, 0, 4, and then 2, 1, 4. So you can see that these are specified as the rows of our table. And then of course we end everything with a semicolon. Okay, so this specifies all our problem data. Okay, so now let's go back to the model. In the model file, after you specify all these parameters, you specify your decision variables just like we did before the first example. So, but in this case, instead of specifying each variable in a separate row, we just say that the variable x, j, is given for every j in the set P, which is the set of products. So for each product, we will have a separate non-negative variable. Okay, so and then next we maximize the objective that we denoted by total profit. And you see, instead of spelling out the objective explicitly, we just say that the objective is given by sum of Cj's xj's for each j in the set P. So see, this is a very compact representation. And again, whenever we change the data in the model, so let's say if you want to add some products or some resources or modify some data in the tables, all you need to do is modify this dot file. You don't touch the model file. All right, so and finally, you specify the constraints. So we have subject 2, and then you'll have the resource constraints for each I in the set R. So we'll have as many resource constraints as we have elements in the set R. And as you see from the dot file, right now we have 3 elements: resource 1 constraint, resource 2 constraint, and resource 3 constraint. So, but for each resource type, we have a resource constraint which is given by the summation of aij's xj's over j in P, and it must be less than or equal to bi. Okay, so this is how easy we can specify this model here. So again, we specified all the data in the dot file. And now let's look at the third file we have associated with this problem. So the third file is actually example2.run file. Okay, so let's open this file in the text editor also. And let's see what we have here. Okay, so here we have the commands that we could alternatively specify in the command window for AMPL. So let's say I could type any of these commands here for our model. So for example, look, we solved this problem, right? But it only specifies the optimal objective. So if I wanted to specify the actual values of the variables, I would need to use this command here, display. I could type display, and then I need to specify the variable. Say I wanted to display x1. So it shows me the value of x1 is 2. Then I could type display x2. The value is 1, display x3. All right, so then I could specify whatever I had for the objective. So, well, the objective is already specified here. So we know that the optimal objective is 11, but let's say if I go back to my original example 1, I called the objective obj value. So then to see the value of the objective, I would need to say here display obj value. You see the obj value is 11, not surprisingly. The cool thing about this last file that we opened, so which was example2.run, I already typed all of these commands here. I don't need to retype display every time I need to see something. So let's see what we have here. All right, so we start by resetting the AMPL environment. So this reset command is important because every time you load a new model, there may be problems with the previous definitions of the variables. So you may have an error message that will say that a certain variable is already defined. Okay, so every time you start solving a new model, you want to reset AMPL environment, and you do it by reset semicolon command. So let me try it in the command window directly. So let's say if I type reset here, so then let's try to display objective value now. You see now it says that obj value is not defined because I reset all the variables. Now in order to have this obj value again, I would need to load the model. So look, if let's say I specify the model again and I said example1.mod, so this is again the first example that we considered. Now if I try to display the obj value, I have 0 because when I just loaded the model, I haven't solved it yet. And the initial value, the default value for the variables for which we didn't solve the model yet is 0. Okay, so that's why we have 0 here. But again, if I solve the model, after this, if I display the obj value, now it became 11 because this is the optimal value we obtained after solving the model. So let's go back to this run file and the second example. So we reset the environment first, then next we load the model. So you see, before we did this in the command window, so I typed model example1.mod, but for the second model, because now my second model consists of the mod file, and it also consists of the data file, which is example2.dot. So let me actually type all of these things in the command window just to show that we could do it this way as well without creating this run file. So let me reset first, and then model example2.mod. So this loads the second model. So, but again, if I look at the second model, so let me close the first one. In example2.mod, see, we don't specify the values of the parameters explicitly, so we definitely need the dot file in order for this model to make sense for AMPL. So that's why we go here and we type up the next line that we had here in the .run file. For data, we use example2.dot file. Okay. So then next, here we specify the solver with which we want to solve the model. You see that this is optional. If I don't specify the solver, then AMPL software will select the default solver that they use, which is Minos. But I want to use Gurobi, okay? So I'm gonna specify the solver to be Gurobi. So option solver Gurobi. And then finally we solve the model. We can see that again the optimal objective is 11. So you see this is the same example as we used in example 1, but now it's just represented differently. Now we split it into 3 files, .mod, .dot, and .run, but I haven't used .run yet, so I'm just showing to you that whatever I type in .run file, I could have typed it directly in the command window, so the result would be exactly the same, but it's always convenient to use this .run file so I don't need to type all these things over again every time. So, and then look, the last line here is to display X, your optimal values for the decision variables, and total profit. So I could type this here as well, display X, total profit. So, and this outputs the optimal values for the decision variables and the optimal objective value. So, but now actually, instead of typing all of this in the command window, all I need to do is to say include example2.run. As you see, this will execute all these commands one by one, just like we specified them. All right. So we solved the model and we obtained the output in the form we wanted. In the distribution that we have on eCampus, along with all the solvers, we have a folder here, AMPL IDE, which is for integrated development environment. So if you go in there and run AMPL IDE, it provides a more user-friendly interface with AMPL. So where instead of just opening the command window, it looks like a more polished software. You can actually use a built-in text editor, and you can open files and run the commands pretty much at the same time. All right, so let's see how it looks like. It's kind of slow, so that's the downside of it. So I would still prefer to use the command window for the speed. So as you can see, it takes a while for this thing to load. Okay, so but once it's loaded, let's see how it looks like. So here you see the command window similar to the one that we already saw when we just ran the AMPL. And there is a text editor on the right. So here you need to specify your working directory. So you can open files that we already created. So I think I had it in downloads. Here we have example 1, example 2. So let's look at the example 2. So let's say this is example2.run. You can open a bunch of other files here as well. So let me open all 3 files representing example 2. So here you have the mod file and the dot file. So all 3 of them are here. So now if I type, let's say, include example2 dot run. So let's see what we get. So it says that it cannot find file example2.run because we didn't specify the path to the working folder. So I need to select the right folder. So it's downloads, and then AMPL. Yeah, this is the folder where all the files are located. Okay, so example 1, example 2. Okay, so let's try it now. So now we can see that we were able to solve the model. Okay, so it's important to specify the path to the current directory correctly. All right. Okay, so in addition to solving all of this on your computer, downloading the files that I gave you for AMPL, and as I told you, all of this is going to expire as soon as the course is over. So we have a license that is unlimited in terms of the scale of the problems that you can solve. but there is a limit on time you can use it for. So, but there is actually an excellent free online tool that you can use to run, AMPL codes. So it's Neos server. So let's find where it is. So here is Neos server for optimization. So this server actually provides access to a bunch of solvers, so you can use all these solvers that are provided with the AMPL distribution for free online. So you need to submit your jobs online, okay? So you go to submit a job to Neos, and there are a bunch of optimization problems that you can solve and many different software packages. So here you have, let's say, global optimization, network programming. So we need to look at linear programming, and the solver we are going to use is Gurobi, and you can provide inputs in several different formats. So there is AMPL that we are using, so there are others. For example, GAMS is another algebraic modeling language where you can specify your models. Then there are several other formats that are standard for many solvers. But we go to Gurobi and AMPL input. And the nice thing about it is, it provides also the links to the different options that you can use with the solvers. So there is a description, and they provide the links to AMPL pages where they describe different options that you can use in order to do many different things with your software. For example, well, there are a bunch of examples here. You can look at the example section on the AMPL website, where they provide many different examples implemented in AMPL. So see, there are many different models that are described in the book, which is the AMPL book that you can also download from the same website. Then there are available solver options for AMPL. So you could look at the options. Again, this is a link to the AMPL website. If we type in Google, let's say Gurobi AMPL options, let's see what we get here. All right, so here are the AMPL Gurobi parameters. Parameter reference, okay, so here it is. Okay, so here there are a bunch of options that you can use. But again, our goal here is just to get started. So now, how do we use Neos server to solve our models? For AMPL, there are three inputs again. So you have the model file. All right, so we choose our example2 here. So the model file is example2.mod. Then we specify the data file, which is example2.dot. And the commands file is our run file. Okay, so it's example2.run, as we used it with the command window, so when we had AMPL installed locally. But for using it with Neos, there are some differences here. So I created a separate file, example2neos.run, to address these differences. Okay, so let me load this here. And then you can specify the email address if you wanted the results to be delivered to you whenever solver terminates. But typically the queues are not too long, and if you submit the job to Neos, you should get the output relatively quickly. So see, it shows the currently running jobs. All right, so let's see how long it takes here. Okay, so you can see that actually we got the outputs very quickly. And as you can see, these outputs here actually include the sensitivity analysis results. So this is because the way I specified the options and commands in this .run file, I actually included the commands to perform the sensitivity analysis. So I'm going to get to this run file in a moment. So let's see how it looks like. Look, here we have example2 neos.run, and let's see what the differences are compared to the original one. So actually, let me open also example2.run and compare the local version versus the Neos version. Okay, so as you see, here we don't reset the AMPL environment because it's done automatically by the NEOS server. Okay, so and look, I commented the reset part, so I could just delete it, but I left it there just to show the difference. Then I also commented the model loading and the data loading. So you see, because on the NEOS server, remember, we have 3 inputs, and on the server they already assume that whatever you provided for the mod file and dot file are gonna be the mod and dot file that need to be used with your run file. So there is no need to specify model and data again. In fact, if you do specify them, you'll get an error message because model and data files are already defined by NEOS. These are the files that you uploaded. Okay, so now option, we had the solver Gurobi, that was a local solver that we used that came with the distribution, but on NEOS they use a different version of Gurobi solver, so you have Gurobi _ AMPL. Another thing is that when we perform sensitivity analysis, so next what we do, we specify options that turn on sensitivity analysis. So before we turn on sensitivity analysis, we turn off the pre-solve option, so we set it to 0. By default, this pre-solve option is set to 1, and it's used to actually simplify the model before it is fed to the solver. And we don't want that because when the model is simplified, the variables are redefined and so on. And we want to do the sensitivity analysis on the original variables, so we don't want any pre-solve here. So that's why we turn the pre-solve option off. And we turn on the sensitivity analysis option. So we have option Gurobi options. So this is a solver-specific option that we specify for Gurobi. So you have Soln sense 1 set here. Okay, so this is solution sensitivity is turned on. All right, so then we have the same solve command as we had before, so this will solve the model. But then when we display the results, look, you display not only X and the total profit, but also, well, these are options that are not really related to the sensitivity analysis. So when you say here resource constraints slack, so let's see what this output in our solution. Okay, we have here first in the output that we obtained on NEOS server, so we had the values for the quantities of product 1, 2, and 3 to produce. Then we had the total profit. So and here we have the resource constraints. This actually specifies the optimal values of the dual variables. So because remember, the dual variables correspond to each constraint. So you have resource 1 is 1.5, so this is the optimal value for the first dual variable, the second dual variable, the third dual variable. So then resource constraint slack, so that we specified here with dot. So you have this suffix, as we call them, that you put after the dot, slack. So this specifies the slacks for each constraints, for each of the constraints. So the first constraint had a slack of 0, the second had a slack of 0, and the third had a slack of 3. And after that, we specify the sensitivity analysis results. As you see, first, we specify the sensitivity bounds for the constraints. So these 2 lines here. And then look, what we have here is sense RHS LO, sensitivity, right-hand side, lower bound on the right-hand side, such that the current basis remains optimal. And for this suffix, you have sense RHS high. So you replaced low with high to obtain the upper bound on the right-hand side, such that the current basis remains optimal. So then if you look at the output, here is what we get. So resource constraints, the lower bounds for right-hand sides were 2, 0, and 5. And then for the upper bounds, we got 10, 12, and infinity. All right, so then finally, the last thing we output here is the sensitivity bounds for the objective coefficients. So for that, we display X and then dot, and for the suffix, we use sense for sensitivity, then obj for objective, and low for the lower bound on the coefficient value in the objective, such that the current basis remains optimal. And then similarly, sense obj high, specifies the upper bound on the objective coefficient such that the current basis still remains optimal. And here we see the outputs. So for product 1, let's say the coefficient must be in the range between 3 and plus infinity. Then for the second coefficient, for the second variable coefficient, your bounds are between 0 and 8. And finally, for the third one, the bounds are between negative infinity and 633. All right. So this is how you do sensitivity analysis with Gurobi solver using the NEOS server to output the results. Now let's try to actually do the same on the local installation of AMPL. Previously, we actually didn't have the sensitivity analysis performed in this run file. So let's make the changes to include the sensitivity analysis. So I need to copy these options for pre-solve and then specify solve sense 1. So we need to perform the sensitivity analysis. And then let's display all these outputs that we displayed on NEOS server. So now we are going to do it locally. All right. So let me save example2.run. And let's go back to the AMPL IDE. And let's see example2.run. Now you see it's different, so we added some lines. So let's see if it will work here. So we go back to AMPL command window and include example2.run. And you can see that you got also the sensitivity bounds just like we did on the NEOS server, so everything works fine. And finally, let's do the same with the command window IDE. Again, it's nice and user-friendly, but sometimes it may get kind of slow because a lot of unnecessary stuff that is used to make it user-friendly. So let's run AMPL here, just a pure command window. So you do include example2.run. And here we get the same results. All right. Well, this is all I wanted to tell you about AMPL in this introductory lecture. And of course, you are encouraged to go back to the website, look at the many different options that you can have with these solvers. And you can explore all these solvers, not just the linear one, but there are other solvers as well. In particular, global optimization solver that deals with different problems. There is a convex optimization solver and so on. And I strongly encourage you to learn more about these different solvers. They're very practical and are used by many companies. So knowing these solvers will be a big plus for you and may help your career.